The recent discovery of a significant magma body beneath the Cascade Volcanoes has left scientists at the US Geological Survey both astonished and alarmed. Long considered dormant or sleeping, these towering giants of the Pacific Northwest are now the focus of renewed scrutiny, as new data reveals a hidden reservoir of molten rock, simmering deep below the surface. This unexpected finding challenges previous assumptions and raises pressing questions about the true state of volcanic activity in the region. Advanced seismic imaging and satellite-based monitoring have detected anomalies that point to active magma movement, an indicator that the crust beneath these ancient volcanoes is far more dynamic than once believed. For decades, the Cascades have appeared tranquil, but this recent breakthrough suggests that powerful geologic forces have been quietly building beneath their serene facade. The scientific community is now racing to understand the implications, knowing that past eruptions in this range have reshaped entire landscapes and posed grave risks to surrounding communities. The long-standing scientific debate over whether magma can linger in the Earth's upper crust beneath volcanoes for extended periods or only ascends shortly before an eruption has taken a significant turn, with new findings from the Cascade Range. Recent research indicates that in this region magma reservoirs may remain beneath volcanoes for thousands of years without erupting. These large, partially melted bodies of magma appear to be a persistent feature throughout a volcano's lifespan, not just a precursor to imminent activity. Thanks to recent enhancements in the US Geological Survey's seismic monitoring network across the Cascade Mountains, researchers have been able to track the passage of seismic waves from distant earthquakes with unprecedented clarity. These seismic waves slowed considerably, by as much as 70%, as they moved beneath volcanic peaks like Mount St. Helens, Mount Rainier, Lassen Peak and others. This significant decrease in wave speed could not be explained solely by temperature variations. Because seismic waves travel more slowly through liquids than through solids, the slowdown strongly indicates the presence of partially molten magma reservoirs 5 to 15 kilometers, 3 to 9 miles, beneath the surface. The study identified such reservoirs under several volcanoes, including Mount Rainier, Mount St. Helens, Mount Hood, Newberry Volcano, Crater Lake, and Lassen Peak. Interestingly, no similar seismic signatures were found beneath Mount Shasta and the Three Sisters, but researchers suspect this may be due to a lack of dense seismic instrumentation in those areas. Notably, surface inflation near the Three Sisters suggests that magma activity may still be present there, even if not yet fully detectable by current methods. These subterranean magma bodies are not vast underground lakes of molten rock. Instead, they are zones of porous stone infiltrated by molten material. An eruption becomes possible only when the melt fraction surpasses 35%. The researchers estimate that the melt content in these chambers ranges from 3% to 32%, which remains below the threshold for eruption. Even at the upper end of that range, such a state could persist for decades or even decrease, influenced by shifting geologic conditions. Importantly, there are currently no signs, such as increased seismic activity, indicating that any of these magma bodies are on the verge of erupting. While the Cascade Range benefits from sophisticated monitoring, much of the volcanic world remains veiled in mystery. Globally, many volcanoes lack the instrumentation required to detect these deep magma reservoirs. The application of similar seismic imaging techniques elsewhere could significantly enhance scientists' understanding of volcanic systems. By better mapping the hidden architecture beneath volcanoes, scientists can take crucial steps toward anticipating future activity. The Cascade Volcanic Arc stands as a breathtaking geological formation, stretching more than 700 miles from southern British Columbia through Washington and Oregon to northern California. This dramatic chain of peaks, including the iconic Mount St. Helens, Mount Rainier, Mount Hood and Mount Shasta, is a vital segment of the Pacific Ring of Fire, one of the planet's most volcanically and seismically active zones. These soaring mountains owe their existence to the slow yet relentless subduction of the Juan de Fuca Plate beneath the North American plate. Over millions of years, this tectonic collision has given rise to more than a dozen major stratovolcanoes and countless smaller volcanic features. The snow-laden summits feed the rivers and lakes that support intricate ecosystems, provide drinking water and enrich soils that have sustained human societies for thousands of years. Beneath this tranquil facade, however, lies a powerful and persistent force. The Cascade Volcanoes are not remnants of a bygone era. They are active, dynamic systems with the potential for sudden upheaval. In recent decades, scientists have detected signs of renewed activity: earthquake swarms, subtle ground deformation and emissions of volcanic gases suggest that the magma chambers deep beneath the surface are far from dormant. The explosive 1980 eruption of Mount St. Helens, which obliterated vast areas and dramatically altered the mountain's profile, remains a sobering testament to the destructive capabilities hidden within these peaks. Today, other volcanoes in the arc, such as Mount Rainier and Mount Hood, are displaying early signals that raise concern. These signs highlight the importance of persistent scientific observation and public preparedness. The Cascade volcanoes are not simply majestic elements of the landscape, they are complex, volatile systems capable of unleashing powerful eruptions with little warning. As subtle geological tremors ripple through the range, they serve as both a warning and a wonder. The same processes that create such awe-inspiring beauty also harbour immense power. To coexist with these natural giants requires not only admiration but also vigilance and respect for their unpredictable nature. Mount St. Helens, whose name is etched deeply into the history of volcanology, experienced a catastrophic eruption in 1980 that sheared more than 1,300 feet off its summit and transformed the surrounding region into a wasteland. For years, the fractured mountain stood in eerie silence, a towering reminder of the forces that had once reshaped it. Many believed it would remain quiet for generations. That sense of calm was shattered in 2004. The year began without incident, marked by low seismic activity. Then, on September 23rd, a sudden burst of earthquakes signalled a dramatic change. What began as a minor tremor soon escalated into a rapid swarm of seismic events, with quakes occurring every minute, some registering magnitudes of 2 or 3. What was initially dismissed as a fleeting disturbance quickly evolved into a significant geologic event. By October 1st, 2004, global attention had turned toward Mount St. Helens. On that day, a fissure suddenly split the crater floor, triggering an eruption that propelled ash and steam nearly 12,000 feet into the atmosphere. Glaciers cracked and shifted under the immense force of rising magma. While smaller in scale than the catastrophic 1980 eruption, this event held immense scientific importance. Despite being the most closely monitored volcano in the United States, Mount St. Helens had reawakened with almost no warning, defying established expectations and shaking confidence in the ability to forecast volcanic activity. This unexpected eruption exposed a critical gap in understanding. Lava had ascended to shallow depths without being detected. For volcanologists, it was a sobering revelation and an invaluable opportunity to re-evaluate existing theories. The incident sparked urgent questions about the Cascade Range's many other volcanoes. Could they too erupt with such little warning? What made this eruption so elusive to prediction? The potential danger posed by the volcanoes of the Pacific Northwest remains significant. With dense populations living in their shadow, the consequences of an unexpected eruption could be severe. In this volatile region, science stands as the primary safeguard. Researchers, using a combination of cutting-edge technology and exhaustive fieldwork, are striving to decode the complex behaviors of these restless giants, uncovering as many new questions as answers in the process. In the backcountry 25 miles west of Bend, Oregon, geologist Dan Zurisin and a dedicated team of scientists are pursuing signs of renewed activity at the Three Sisters Volcanic Center. The landscape appears serene, but data tells a different story. Central Oregon's Three Sisters region is known for its volcanic history. And although no eruptions have occurred in recent memory, satellite measurements have recorded consistent ground uplift, about 1.5 inches per year since 1998. Something is stirring nearly 4 miles beneath the surface, and the scientific team is determined to find out what. Zurisen specializes in ground deformation, a phenomenon often linked to magma movement. The subtle swelling of the Earth around South Sister could suggest that magma is accumulating deep underground, possibly the early signals of future volcanic unrest. In hindsight, such clues would have been invaluable prior to the 1980 eruption of Mount St. Helens, when the lack of effective monitoring left scientists blindsided as magma surged toward the surface. Today, technological advances have revolutionized volcano monitoring. Tools like radar interferometry allow researchers to detect minute changes in the Earth's surface from space. Interferograms, radar-based images, highlight ground deformation that would otherwise go unnoticed. At the Three Sisters, these images have revealed a striking bullseye pattern centered near South Sister, a clear sign of underground activity. In response, scientists have ramped up investigations, conducting yearly ground surveys and installing GPS stations across the rugged terrain. Mike Lisowski, a member of the field team responsible for deploying these GPS units, emphasizes the demanding nature of the task. Navigating difficult landscapes, the team targets both the heart of the uplift and areas farther out to map its full extent. The data collected offers essential insights into the rate and scale of ground movement. While at least one swarm of small earthquakes has occurred near the uplift, a possible sign of magma-related stress, experts remain cautiously optimistic. The Three Sisters region has a history of both fluid basaltic flows and more explosive eruptions, but current assessments suggest that even in the event of renewed volcanic activity, the threat to human life is low. Disruption to the natural environment, however, could be significant. Still, as Zurisen explains, the real value lies in understanding the patterns of unrest, each signal a puzzle piece in the broader effort to anticipate nature's next move. Scientists closely track subtle surface changes at the Three Sisters Volcanic Center using high-precision GPS instruments. These tools measure minute shifts in the Earth's surface by calculating the distance between fixed ground-based receivers and orbiting satellites, achieving precision down to mere thousandths of an inch in 3 dimensions. Since 1998, the uplift in the region has totaled just 8 inches, an almost invisible transformation over a vast 10-mile expanse. Yet, this imperceptible bulge has not gone unnoticed by researchers. Despite standing directly on the rising ground, hikers often inquire about the bulge's location, unaware that they are already on top of it. Such gradual changes unfold quietly, offering no dramatic visual markers but holding profound geological implications. This subtle deformation stands out precisely because the Three Sisters wilderness remains otherwise tranquil. However, remnants of past volcanic events are scattered across the landscape, silently attesting to the area's volatile history. Some geologists suggest that such bulging may be a natural part of the Cascade Range's volcanic rhythm, a cycle of magma intrusions that do not necessarily lead to eruptions. Others believe this activity might be an early sign of a larger geologic awakening. The reality is that long-term volcanic behavior remains elusive. With only a few decades of modern observation, scientists recognize that they may be witnessing an ordinary episode in a vast geological timeline, or perhaps a critical precursor to future activity. Central Oregon's volcanic legacy, however, paints a more turbulent picture. The region has produced more lava than any other section of the Cascades, and the Three Sisters Volcanic Center is particularly distinct for its scattered vents, as opposed to the towering centralized peaks of Mount St. Helens or Mount Hood. This distributed activity bears striking resemblance to other volcanic systems around the world. For instance, recent eruptions in the Galapagos Islands echo the lava flows from Newberry Crater some 1,300 years ago. Similarly, the intense, vent-driven outbursts of Hawaii's Kilauea reflect the kind of volcanic force that once inundated Oregon's Mackenzie Pass with molten rock 1,500 years ago. These parallels underscore the persistent potential for renewed volcanic action in the Pacific Northwest, though the exact timing and location remain unknown. Forecasting volcanic eruptions continues to be one of Earth science's most formidable challenges. A volcano may slumber quietly for decades, showing no outward signs of unrest until, within a day or even hours, it suddenly springs to life. Even with modern tools and years of data, the signals that foreshadow eruptions are often ambiguous and fleeting. The 1989 eruption of Alaska's Redoubt volcano followed a rapid escalation of seismic activity, culminating in a powerful blast just 24 hours after the initial tremors. In contrast, Mount St. Helens in 1980 gave a much longer warning, with 2 months of seismic rumbling and ground swelling that preceded its devastating eruption and massive landslide. These contrasting timelines reveal the unpredictable nature of volcanic behavior. Examining volcanoes that appear dormant, like the Three Sisters, might seem like a purely academic pursuit, but the haunting legacy of Mount St. Helens underscores just how high the stakes truly are. When Mount St. Helens erupted catastrophically on May 18, 1980, it shattered expectations and redefined the field of volcanology. At the time, monitoring relied on rudimentary tools, basic seismographs, binoculars, and field observations. After lying dormant for 123 years, the mountain's violent awakening turned daylight to darkness, claimed 57 lives, and unleashed devastation across southern Washington. Yet, from this tragedy came a profound leap in understanding. The eruption exposed hidden clues embedded within the crater walls, evidence of past landslides and lateral blasts that had been overlooked or inaccessible before. It became clear that such cataclysmic eruptions were not anomalies, but part of the volcano's deep-seated history. In the aftermath, public demand for improved monitoring surged, and Mount St. Helens was transformed into a world-class natural laboratory. Today, scientists use cutting-edge technology to study the volcano's evolving behavior. Digital elevation models track topographic changes, charting everything from lava dome growth to the birth of new glaciers. These tools reveal dramatic shifts in the landscape, providing real-time insights into Mount St. Helens' persistent activity. Since October 2004, the volcano has remained restless, its subtle changes punctuated by periodic bursts of steam and ash visible from miles away. Sophisticated heat-sensing cameras now capture the movement of magma beneath the surface with unprecedented clarity. At temperatures exceeding 1,000 degrees Fahrenheit, this molten rock slowly pushes upward, building a lava dome that now towers nearly 1,000 feet and spans half a mile across. The sheer scale of this transformation is staggering. If the city of Portland were placed inside the crater, it would be dwarfed by the 2 massive magma domes within. One was formed in the 1980s, while the other, a pale grey mass, has emerged over the past year and a half. At the current rate of growth, Mount St. Helens could reclaim its pre-1980 elevation within just 5 decades, an extraordinary pace of reconstruction for any volcano in recorded history. What makes this ongoing eruption particularly fascinating is the nature of the magma itself. Unlike the explosive material from the 1980s, today's magma is cooler, thicker, and significantly more crystalline. It carries fewer volcanic gases and does not erupt straight up into the sky. Instead, it appears to have been diverted beneath the older dome, now forcing its way to the surface at an angle. This atypical pattern offers researchers a rare real-time glimpse into the mechanics of lava extrusion, sparking fresh questions about volcanic behavior and structure. To safely study this volatile environment, scientists have turned to ingenious innovations. One of the most significant advancements is the deployment of spiders, rugged spider-like instruments designed to endure the extreme conditions inside the crater. Equipped with seismic sensors, GPS systems, and remote telemetry, these devices allow researchers to gather vital data from areas far too dangerous for human presence. Delivered by helicopter to the active dome, the spiders stretch their metal legs across unstable ground, recording seismic tremors and ground deformation with unwavering precision. However, the interior of the crater is merciless. These machines frequently return charred and broken plastic components, melted cables, scorched sensors, and shattered sensors due to the relentless heat and mechanical stress. Yet, despite the toll, they remain an essential tool for modern volcanology. Their endurance and the data they transmit provide scientists with a safer, clearer view of an ever-changing landscape. offering crucial knowledge that may one day save lives. Inside the crater of Mount St. Helens lies a dramatic juxtaposition, a smouldering magma dome sitting beside a glacier nearly 600 feet thick. This icy mass is not just a passive bystander, it plays a potentially dangerous role. As the searing heat from the rising magma melts the surrounding ice, pools of water begin to accumulate. When this water meets hot rock, it can create volatile, steam-driven explosions, posing a real hazard. Despite close observation, there remains no definitive warning as to when the next significant volcanic event might occur, making future eruptions difficult to predict. Externally, the surface may appear calm, with only a relatively cool layer of hardened lava visible. But beneath that facade, temperatures soar to between 600 and 700 degrees Celsius, an intense heat situated alarmingly close to the crater's frozen wall of ice. Given the extreme dangers of venturing into the crater, scientists rely on remote monitoring tools known as spiders, mobile sensor platforms capable of recording seismic activity and gas emissions without risking human lives. Unlike the catastrophic 1980 eruption, which happened during favorable weather conditions, the renewed volcanic activity in 2004 began just as autumn faded into winter, bringing shorter days and significantly more treacherous working conditions. Yet researchers remain vigilant around the clock, maintaining an uninterrupted flow of data from the mountain. Modern instrumentation has ushered in a new era of volcanology. Real-time information streams in constantly, allowing researchers to stay connected to the volcano without ever stepping foot on its flanks. When seismic alarms are triggered, often in the middle of stormy nights, scientists can remotely access vital information, including ground deformation and seismic shifts, enabling them to respond quickly and accurately. Thanks to this technological leap, Mount St. Helens has become the most extensively monitored volcano on Earth. In 2004, this network of sensors made it clear that the eruption would differ from the explosive devastation of 1980. These insights helped ensure public safety and highlighted the effectiveness of contemporary monitoring systems. However, knowledge remains sparse for other peaks in the Cascade Range, such as Mount Hood, Mount Jefferson, and Mount Rainier. Prior to 1980, Mount St. Helens was just as poorly understood, and now the challenge is to avoid repeating that lack of preparedness elsewhere. History has demonstrated how rapidly volcanoes can shift from silence to chaos. If, for example, Mount Rainier began rumbling in February, there would be little time to react unless monitoring equipment had already been deployed the previous summer. This underscores the need for continuous proactive research and preparedness. Identifying which Cascade volcano might awaken next could offer immense value, not only to science, but to public policy. With such foresight, development in at-risk areas could be curtailed, potentially sparing communities from disaster should an eruption occur within the coming decade. Despite centuries of inquiry, the deepest questions surrounding volcanic activity remain unsolved. Scientists continue to seek answers about what truly drives eruptions and fuels these massive subterranean forces. Progress comes slowly, often measured in mere feet per day, but the pursuit continues. Volcanology, still in its scientific adolescence, carries vast potential. Yet the public must understand that even with all our instruments and insights, much about these colossal forces of nature remains shrouded in mystery. In the Pacific Northwest, Mount St. Helens continues to captivate those who live in its shadow, a constant reminder of Earth's dynamic forces. The mysterious bulge beneath South Sister remains an enigma, symbolizing the hidden power beneath the surface. These geological features command attention not just for their beauty, but because they represent phenomena that science has yet to fully decode. Each day, researchers comb through the Earth's crust in search of clues, and each night they pore over data, striving to understand the secrets that lie beneath the Cascade Range. Across the scientific community, the recent reawakening of Mount St. Helens has reignited passion and purpose. For many volcanologists, witnessing such events firsthand is a rare and defining moment in their careers, an opportunity to transform experience into knowledge and to mentor a new generation. Despite remarkable advancements in volcanic science, much remains unknown, keeping the field vibrant and filled with potential for future discoveries. While experts continue their vigilant monitoring and investigation, public awareness and preparedness remain essential. The exploration of these powerful natural systems is far from over. For those intrigued by the mysteries of the Earth, staying informed is not just educational, it's vital. Continue following for more insights into the fascinating world of geology and the ever-changing landscape of the Cascades. Stay safe, stay curious, and keep exploring.